Hey robot makers, hope you're having a good day so far, good weekend so far. So do you want to know all about amazing let me get this right, Mecanum Wheels? They are mind-blowing when you first play with these. And also motor encoders as well. The two combined make a really, really cool robot. So I built a new robot using these called Rover. So if you want to learn all about that, then this is the show for you. So let's dive straight in. My name's Kevin. Learn with me as we build robots, bring them to life with code, and have a whole load of fun along the way. Okay, let's get over to our keynote and have a look what it's all about. So yes, the session goals for today is we're going to have a look at Rover, this little robot that I built quite recently. I'm going to talk to you about some of the design decisions I've made in that. We're going to look at Mecanum Wheels, how they work. We're going to even try and build some of these in Fusion 360. We're going to look at encoders as well. This is something I learned about quite recently too, specifically for making your robot really, really precise when it comes to positioning. We're going to dive into Fusion 360 and have a look at the robot itself, and then we're going to have a look at a pre-recorded demo that I did for this. We'll talk about that later too. Okay, so meet Rover. So Rover is the little robot there on the right hand side. The STL files will be available very, very shortly. I just need to upload them to the GitHub repository and write a little article, a little intro on kevsrobots.com all about that. So you'll be able to have at them and print out your own versions of this. And I've done a few iterations of this already. It didn't need too many actually. So this is like the original prototype I had. It had the same kind of rangefinder thing originally as my Explorer bot, which is just here. But I decided I want something a little bit more interesting than that, so I worked on something, and we'll have a look at that too. So yes, Rover has Mecanum wheels. So Mecanum wheels are really, really cool. They're quite quirky. I'm not sure how widely they use in industry. I don't know if they have like a limited use, but on robots they are really, really cool. We're going to have a look at some new N20 motors as well, which have encoders built in. The encoders mean that the Rover has extremely precise movement, so we can place it wherever we like without using any kind of like MPU or measuring device. It's just the encoders built onto the back of the motors. It has a rangefinder just for measuring distances. At the moment, you can see on that diagram, I've actually not got that plugged in, but I have got some new cool things called level converters. I'll just get this one out of here and I'll show you this little thing. So this is a tiny little board from, I think it's Spark Fun. I'll show you this little board here. So this tiny little board, it's basically got two sets, like an input and an output. So you can put 5 volts in and you get 3.3 volts out. So if you're doing something that requires like a Raspberry Pi Pico and you don't want to blow the chip up, you can drop it down just by using one of these little boards. So these are really cool. This is what we'll need to do if you want to use a rangefinder with a Raspberry Pi Pico or any board that uses 3.3 volts. So that's something that I've learned quite recently. I can't wait to plug that in and have a play with that. And then for the battery pack, I'm using the exact same battery pack that is used on the Trilobot. So it's one of these 2-power USB battery packs. In fact, I've got them on the desk there right next to each other. If I go to that camera there, you can probably see I've got Rover there, I've got the Trilobot there. I've also got Explorer just here next to us as well. We're going to have a look at that in a second. Okay. So let's have a look on the next slide. So yes, one of the important design decisions I made when I was making Rover is to make sure that the wheels and the centre of the robot are kind of aligned. So this means when we turn our robot round, or whenever we're doing anything to do with the motors really, the centre of mass, the centre of the robot is the exact centre between the wheels. Just means that when we move the motors like in opposite directions to make it will turn very precisely with that middle point there. Just makes it really easy to calculate stuff as well. So it's kind of mirrored. The only difference is the back of the robot down here has got like a flat bit and the front bit has got this rounded bit where the rangefinder sits. That's the only two differences really. Cool. So then component wise, what actually makes up our Rover? So we have 4 Mecanum wheels. So you can get these from online stores. I got them from Pimoroni. I think they're about £24 UK, and they come in different colours. You can get like black, red, green, yellow, and so on. You can print your own, and we're going to have a look at that in a minute shortly, and we'll also have a look into this in Fusion 360. I've started building my own version of these just to see how easy and feasible this would be. But these ones are really high quality. All these spindles on them, which we'll have a look at, are really, really smooth, feel like they have like a bearing on them so that they move even if they're under sort of quite a bit of pressure. There's the HC SR04 rangefinder. Now, I did find online a really cool rangefinder that's got LEDs behind it, and depending on the distance detected, they'll change colour. They're quite cheap on AliExpress, but getting them shipped over to the UK was just like extortionately expensive and would take weeks as well. So I might be looking for an online version of that I can get hold of in the UK quite easily. But at the moment, yes, just a HC SR04 rangefinder, the ones that we've used in all our SMARS robots and so on. We have 4 standoffs, so I've got a whole load of stands. I've got a little box full of them up there in my cabinet. And they're just to make the board that's going to be driving all this just sit slightly above the chassis. And it means we can sort of stack them, very much like I've done with Explorer here. So if you look at Explorer, you can see there all the different standoffs. So on that particular one, we've got like a Raspberry Pi Zero underneath, we've got an Explorer hat, and we've got another chassis to put the LiDAR on top of. So that's the kind of thing I had in mind when designing this. And that design works really well on Explorer, so I didn't want to sort of deviate from that because it works. So it is a new board that I've designed, but it's based upon that. We've also got 4 motor holders. You can buy motor holders commercially. They're little brackets that hold the N20 motors in place. And they're quite neat. They have like a little hex nut on one side that's sort of captured, and then the bolt goes through and tightens them in place. And I copied that design on Explorer, and this is what I want to release as the STL files. You can see there, these little yellow motor holders hold the motor in place, and they have a little captured hex nut. If I just get that in place there, get that to zoom in without looking at my face, you can see there. And then on the other side, it's just like if we can get a good shot of that. They're just in there, little nuts and bolts. So they work really well. They keep the motor really, really solidly in place, and you can 3D print them. So all you need to bring along to the design then is just the nut. I think it's a 3M nut and an M3 nut, sorry, and a little bolt to go with that. There's the 4 N20 motors as well. The gearing ratio on that is probably something to consider. So on my overhead, if I go over here a second, I've got a whole load of N20 motors here. So I think these ones are all the exact same. And these ones are very slightly differently geared. If I just grab 2 of them and we have a look, we can, if I just hold these up to the camera. Now what you want to look at is the little gearbox on the end of the motors. And you'll see that, if I can get that to focus, you'll see there that they've got a very slight different number of gears. So if you look at where the motor is, let me just get a pencil to point at things. So if you look where the spindle comes off, there we go, off the end there, that one looks very different to this one over here. This one's got like an extra gear there. And that means that the gear ratio, the number of times that let's get back over there. The number of times that the spindle that you could attach the wheel to spins round is different depending on the gearboxes. So that gearing ratio is quite something that's important. And the trade-off is you can have a really fast motor, but it hasn't got much power. So if you had something that was really fast, as soon as it kind of goes up a gradient or has any kind of load put on it, it will start to slow down, possibly burn out if it can't supply the amount of power to keep turning. Otherwise, you can have it really slow, but it's got loads of power, it's got loads of torque, so it'll keep on going no matter what the pressure is on it. So that's the kind of difference between, say, a 300 to 1 ratio and a 50 to 1 ratio. And that'll be important in a minute when we're looking at encoders. And then the chassis itself, like I said, this is the prototype that I worked on. I think this is exactly the same as the one that I've got on my final one. This is just white. And I think I printed this one on the low quality setting just to get it very quickly, whereas the other one was sort of a high quality one. But yeah, so there's just little mounting holes for the motors to go on, the little holes for the wires to come through from the motors. There's these set of little holes there so that we can push these things in place and it'll be held in place there. And what else have we got? And then there's just some mounting holes for a board that will control everything. And the idea is this is like 3mm thick. It's pretty robust, pretty strong, so not a problem. So I've got a question about some of the other motors I've got on here. So these are N20, but these ones have a really long thread on them. And these ones I bought when I was putting together one of the SMARS robots. So one of the SMARS robots has this forklift attachment, and inside there, you can just see the back, there's an N20 motor there with one of these on, and inside here there's just a sort of captured hex nut, and it'll just make this go up and down. There's nothing to stop it when it hits the very top. There isn't any kind of endpoint detection. You just have to know not to do that. But that's what I've got them for. And then I've got some other ones which have the encoder built onto the back, and we'll have a look at those in a bit. Cool. Okay, so Mecanum Wheels. These are really cool. So these are available, like I said, from online supply companies, a bit like P. Maroni, Adafruit, Sparkfun, those kinds of things. You can 3D print your own with a bit of faff. I'm not sure of the quality of the 3D printing ones. I haven't tried out that particular design there, but I did find it on Thingiverse, thing 1203230. And they've got a little screw you can just about see on the picture there. They've got a screw in there just to give it a bit of grip and kind of acting as a bearing on there. But I'm not sure how they will work. They haven't got this sort of round top to them either side, so that they've not got that kind of sideways rigidity. So I'm not sure how much pressure you can put before that just snaps or twists and bends. But the idea on these, as we'll see, is these spindles spin round freely. So if I go to my overhead, I just pick up this robot and show you a bit closer. So these will actually spin round on the axis, and the wheel spins as well, and they are sort of proud, so they are making contact with the floor, not this black part. The yellow part is making contact with the floor. These ones are slightly rubbery to feel. They've got kind of a texture to them, a bit like an earbud or something like that, that kind of shape. And each one of these corners has got a motor on it. Show you there. Each one of these corners has got a motor on it. Okay. So 3D printing your own is something I want to explore, because the idea will be, if you want to buy a pack of these, I think they're about £24 UK if you're buying them in the UK. If you're buying them somewhere else, then the price starts to creep up. So if you had a classroom and you wanted to sort of print out, you wanted to have every child have a robot, that would get pretty expensive pretty quickly if you were doing like a Mecanum project. So 3D filament is pretty cheap, just takes a long time to print out. So that's kind of what I'm thinking there. Can we do something with 3D printing, but try and get it as close to the quality of these as possible? So I think we can do that. So I've been test printing out some little spindles, such as these ones. I'll just hold this one up and let you see. Again, you can just see what that looks like. So it's really small. And the idea behind this, I've got some 3D printed filament here, and I want to be able to sort of push this through and have these spin round on the end of this thing, and this be the thing that is the spindle, the bearing, whatever. A bit like we have on these SMARS robots. So on this SMARS robot here, you can see if I can get that to focus. It's focusing on the cable there. The track there that's in red has got a little white piece of 3D printed filament as the thing that's enabling these wheels to sort of pivot round, these track pieces to sort of pivot round. So that's kind of where I was coming from with this. Maybe we can do something with a wheel, use 3D filament as the actual thing that it spins around. We just need to work on tolerances. So at the moment I push that in, it's a little bit tight. This isn't freely spinning, just like the ones on the Rover. They spin round freely. And I can see that there's like a little metal thing in there, I can hear it. So that's the trade-off there. Maybe we could use like a paper clip, just clip a paper clip. But again, I'm just thinking, if you're going to build this in a school, you want things that are safe and also easy to come by. So, and somebody saying in the chat there, doesn't Richard Bruton do things with wheels? He does all the things with wheels. I think his channel has been nothing but wheels for the past 6 months, and the odd open dog robot. Yeah, I think he's explored pretty much everything you can do with wheels. This is my first experience with them, so I wanted to share this and my take on it as well. So encoders, I think they are a really good thing to have on your motors. It's not something I've played with previous to this project. I have played with the Lego robots, like the Spike kit and the Mindstorms kit and the Inventor kit, and the servos that they have, continuous rotation servos, and they have an encoder built in. And one of the reasons this is really cool is if your robot from a software point of view thinks it's stationary, but the wheels are turning because maybe it's on a slope, then you can detect that. You can read what the wheels are actually doing versus what you're telling them to do. And you can have an algorithm that basically feeds that back into things. So you can actually make it stay still if it's on a hill, or you can make it go faster if it's under load. You can do all kinds of things like that if you've got encoders. So what encoders do is they count the number of revolutions that the motor makes. And this enables really precise positioning of the robot. And the encoders on these ones are attached to the very back of the N20 motor and provide feedback to the microcontroller that's controlling the motor. So the gearing, which we talked about earlier, remember the 50-to-1 or the 300-to-1 and the power versus the speed. The gearing means that the back of the spindle where the encoder is will spin differently to the other end, which the wheel is connected to. So that's something to bear in mind. So the 50-to-1 means that the encoder rotates 50 times for each rotation of the wheel. So the wheel rotates once, that little encoder will rotate 50 times. And that means we've got 50 slices of wheel to look at. We can get that much more accurately. So the little encoders I was looking at just there, I think they're from a company called Polulu. They're available from Pimoroni, and they currently come as a kit that you can solder onto the back of your micro metal gear motors, not Greer motors as I've typed there. They have to have the extended back shaft version. So I think all the ones I've got are not the extended back shaft version. So if I show you that one there, it doesn't have like that spindle is the bit that you plug the wheel onto, but the back piece there doesn't have, on the ones I've got here, the extended shaft. So you need to have them if you want to be able to use the encoders. And this is kind of what the encoders look like when they are sort of soldered on. This one has got a header on it, so we can plug a wire into it, but it's essentially the same as what you're looking at there. If I just hold it that way, it looks slightly different because the six, get my finger out of the way there, the six things are just put together as 2 rows of 3, just for convenience there. But you can get these today. That's on screen there, that's what they look like assembled. You've just got a little ribbon cable, so you've got on there, I think it's like power ground, M1, M2, and I forget what the other 2 are on there, but they're all part of the how to make this thing work. So we'll talk a bit more about this as well. So these particular wheels, these particular encoders use the Hall effect. So the Hall effect is where you have a circuit that can detect something coming close to it, like a piece of metal or a magnet. The resistance will change the closer that thing comes to it, and that's called the Hall or ground effect. So on the wheel, you can see that these 2 circles, and they've got either a piece of metal in there or a magnet, and as they come past these 2 sort of sensors, it can detect that they've gone past there. So that's how you can count that it's rotated. On this particular one, if there's 2 of them, you could see that it's rotated once or twice. And the reason that we have 2 of them is we can infer the direction, because if it goes from one and then the other, we know that it's going that, anti-clockwise. If it goes from that one and that one, then it's going clockwise, depending on which way I'm looking at my finger and you're looking at my finger. So you can detect the direction by having 2 sensors like that. So really simple to get. I think you might be able to get hold of some of these pre-soldered. I've not looked into that yet. So how do encoders work? So on this particular example, I've just got a very simple encoder disc with a hole in it, and I've got like an infrared. You'll just see it pass through there. Infrared beam passing through, and it's getting blocked, and as soon as it goes through, we can have a detector on the other side, and that'll detect that the beam has been broken and therefore count 1 revolution. So that'd be like a really simple version of an encoder, but you can get all different types of ones. Like we said, there's infrared, there's ones that use magnets, there are ones that are optical that detect like a black mark as it spins past. Different types of thing, but essentially it's all the same thing. There's a disc, it has some kind of mechanism mark or encoding on it that can be detected by a sensor each time it rotates round once. And we can capture that through our microcontroller and count some variable up or down. So Mecanum Wheels, this is where things go sideways really quickly. So Mecanum Wheels are made up of these little diagonal spindles. So these little spindles, like this one I've 3D printed here, I'm really impressed with the quality of this for a 3D printed object. Just look how smooth that is. So they have a hole through the middle of them. Again, it's not very easy to get this on camera on shot, but there's a hole through the middle of them there. And the idea there, you have some kind of metal or plastic that goes through and enables that to spin round. Now, when they are working just as a regular wheel, they're just making contact with the ground like a regular wheel would. But when we want to use them to make the robot go sideways, that's where rotating the wheels in opposite directions will make the sort of diagonal part of this sort of kick in. So they then start to spin on the little axes of these little diagonal spindles. We'll have a look at the better animation in a second of that. So we put all these together in like an omni wheel. We fit these in that particular orientation there, and I've got a slide to show you what I mean by that particular orientation, and then we can do some really cool things like make our robots go sideways. So the direction of the wheels needs to point inwards. So I just bring up my little robot here. We look from above there. I get that on shot there. Oops, my battery's just falling out there. So if we look at these wheels, they sort of point towards, just trying to make sure I get that right, they're pointing towards the center of the robot. So that one's pointing that way, and then that one is pointing that way too. If you haven't got them in that orientation, then they're not going to work properly. I think you can, there is an orientation where you can get it reversed, and it just judders quite a bit if you don't do it quite right. But that's the orientation that they need to be in. That will make the Mecanum effect work. So here's another animation that I put together. So this is a forwards. They rotate as you would expect it, like a normal wheels would do, all four of them at the same time. If we want to rotate, then you have one side rotate opposite to the other side, just like you would with like a regular tank robot like this one. And then strafing left, this is where we can make the robot go left or right. So left, well, if we go right, you can see the right hand side are turning inwards, the left hand side are turning outwards, and that's what creates that Mecanum strafe effect, left or right. So if you like these kinds of videos, you want to help me out, you can do something that costs you nothing, and it's to drop me a like on the video. That tells the algorithm that this is a good video and you enjoy watching it. You can also drop me a comment and let me know if you enjoy this. If you've ever played with Mecanum Wheels before, that's something you're interested in doing. And if you're watching this on YouTube, hit the bell, means that you get notified of whenever a new video comes out. And of course, subscribe to the channel, really helps me out too. Okay, so I also do a new video every single Sunday. I live stream, as you're probably watching now, if you're not watching if on this on replay. And yes, it's either Greenwich Mean Time or British Summer Time, whatever 7 PM local time is to the UK when I record this. That's just if you want to join the live stream. We also have a Discord group, so if you want to join our Discord group completely free, just head over to action.smarsfan.com/join-discord, and you'll get the link there to be able to join our Discord group. It's a really growing group of people who love robots. So let's have a look at the Fusion 360 design, and then I'll show you a pre-recorded video of the Mecanum robot in action. So let me just get myself sorted here. I'm just going to open up Fusion. They recently changed the logo on Fusion, and sort of getting used to it at the moment. I'm just going to move that support me thing there, but if you want to help out with the show, you can help out by buy me a coffee. Go to buymeacoffee.com/Kevin McAleer, and that can help pay for all the various different things I need to pay for to support the show, such as the website hosting, the royalty-free music at the beginning, the graphics software Canva that I use to do all the thumbnails and so on, the streaming software that does all the fancy intros and all these kinds of overlays and stuff. That's called Ecamm, and of course all the equipment and cameras, lights, and robot parts. So that's enough of that. Let's get back to it, and I can turn off that widget there. Right, so I've got on screen here a Mecanum wheel that I put together, just modeled because I wanted to sort of have a model to be able to show people. So what I'm going to do, I'm just going to show you this from sort of different angles. That's what it looks like from the side. Obviously from the top it looks exactly the same, and if we go from the front view, it just looks like a regular wheel there. So what makes this sort of unusual is that these things can spin round. So I've created some, they call them joints in Fusion 360, and it's a way we can actually go into this and we can switch off the right and the left side, and we can see what that looks like. And in fact, if I go over here and I animate this, if I just say animate model, it can spin that round and you can see what it looks like kind of inside. So it's unusual that it's really only just the middle of that spindle that's ever making contact with the ground, really. and because it's got ever so slightly like a diagonal plane to it, if ever you make the other wheels push in that direction, it will happily sort of spin the spindle round and then travel in that other direction as well. Otherwise it'll just travel in this sort of straight line direction. So I'm just going to turn these back on so we can see what they look like. In fact, let's turn off the spindles and just have a look what it looks like inside. So you can see there we've got all these different planes where the spindles are connected to. Let's just put them back on there and let us have a look at something else. So this model, that's just one wheel. We can actually switch on all the other wheels and see this kind of in action. So if I switch on a chassis there and then just switch on these other wheels, there's actually a proper model here. So what we can do, we can have a look from the top. Let's have a look in that orientation. And let's now animate the model again. So I think I've got this time. Let me just switch those back on. There's a bit of a quirk there. When you're still animating, it forgets what you've just done. Right. And then in that last Mecanum wheel, we just need to switch back on the left and the right base. There we go. Okay, so if I now animate that again, animate model, you can now see as these wheels turn inwards and these ones turn outwards, this would actually send the robot going, sorry, on your direction that way. So it would strafe left. And let's have a look at that in a sort of different orientation. Oops. Let's kind of go like that. So you can see there, this wheel is spinning round, it's spinning inwardly, and that kind of creates a drag towards that orientation. So I'm trying to get my orientation looking the same. There we go. So we're dragging that kind of orientation. If we reverse that, we can reverse that just by editing this joint on here. So let's just edit that. If I just move, no, it's not actually editing the joint, is it? It's editing the motion link. So let's go for motion link, edit that. Just move this out of the way. So currently I've got them as 360 and minus 360. If I just reverse, well, if I just click reverse on there, and now we try animating that again. Let's try that. I think it will now animate in the opposite direction. Oh no, so they're now both traveling in the same direction. Let's have a look. Yep, so they're now traveling in the same direction. So this has been an interesting thing. What would the robot do there? So that side is sort of traveling left. That one is traveling. So they're all going forward, but the very back one isn't. So it would kind of go forwards, but with a bit of drag from that last wheel there. So let's just go back and edit that motion link again. Stop that, and then we can put that back on there. So what I've done on here, I'll show you this in a second. Just click that off again. When you're creating a joint in Fusion 360, you can join the joints together to create a link. So you can have a motion link between two things. You can either say that they both move the same, they move opposites. You could say that for every turn of one, the other one turns twice, or however many degrees you like. All kinds of things like that. So you can create really complicated kind of gearing things for that. So I just wanted to show you that that's kind of how they work from a mechanical point of view. So yeah, that we've had a look at that one already. That's the ones with the spindles on, with the hole on. That's the new version that I'm just working on. And in fact, if we bring this in, I've made this one a bit more complicated. This is the one that I'm looking to 3D print. So if I just spin this round, so I've got a little plug in there, and if we take the plug out, we can see, if we look into it, let's just grab this. So I was trying to do this without a mouse. There we go. And in there is where we would put like a screw and a nut. Could put the nut in this area and then the screw from the other side, just to attach these two parts together. So we've kind of got a face plate and a base plate. So that's the base plate, and that will attach to the face plate. And I've also put these little sort of holes in there so that the base plate has got something to grip into. So if I just spin that round, you can see that's got the corresponding pins that go into it. So that'll just give it a bit of grip there. So the other thing that this one has got is this one has the holes for the filament to go through. So if I just align that hole there, you can see right through there, that's where the filament would go through and enable that particular spindle to spin round freely. That's a theory. I just need to work on the tolerances. So that could be quite tight, that wouldn't be a problem, but the hole that's inside for the filament, that just needs to have the correct tolerance on there. So I've added some extra things like tolerances so I can play with those and just reprint them out. They're very quick to print out, these things. I think they're about 15-20 minutes to print out one of these spindles, so they're quite quick to test. Getting all this to sort of sit together, that's probably going to be a bit fiddly, and that's why I've made sure that this model is quite robust. So that's why I've got things like this plug to be able to put in there, so that if I damage that, I can replace it. Okay, so that's one of the Mecanum wheels, and then let's have a look at Rover itself. So here we go. So if I go for the chassis and just show you the chassis piece, let's have a look at this from the top, and let's spin that round. So as I was saying, we have very, very simple 3mm thick, essentially a flat plane, so it's quick to 3D print. Hasn't got any kind of features on it. It's just got some pre-drilled holes, if you like, in there. So those two holes are for the motor holders. We've got two holes there for the standoffs and then the motor board, and then we have these slots for the rangefinder to go to. Now originally, if I just get my original design, and let me get Explorer to explain what's going on there. I based the design very much on Explorer. So you can see this robot here that I've designed. This has the rangefinder coming through a single plate, and then there's another plate behind it just to sort of hold that in place. And yes, I absolutely stole this off of the Pimoroni design of their Trilobot. I mean, it's almost a one-for-one copy on there of their design. But I've used 3D printed parts rather than their really solid metal and whatever PCBs are made out of fibre board. So this is why this has got those lots of slots, and you can also see on this Explorer these 3D printed motor holders, and they hold the these motors don't have the encoders on the back, they're just regular motors with a plus and negative on there, but you can see the bolts that are holding everything in place there, and on the other side we've just got some I think they're like little hex nuts, screws that screw everything in there. But this one just has the regular moon buggy wheels. And then on Explorer, on Rover, I've used the commercial ones available, and you can see there they work exactly the same way. They've got a little capture nut in there, and they have a screw that screws onto the other side. The only difference on this particular one is I do have the motors that have the encoders on, as you can see there, and they also come with a really nice, if I just get that to focus in there, they come with like a really nice cable there that can plug in to the board. And then we have the really nice sort of quite organic design of rangefinder. So you can see the rangefinder is quite rounded, looks a little bit like a frog, I think. It's got this nice sort of shape to it on there. So let's have a look at that in Fusion as well. So if we go over to the rangefinder holder, which is the next one I designed, let's have a look at this. So the reason I wanted something a bit more chunky is I just thought we could print something out that's more three-dimensional rather than just you know, a solid flat piece like so. These are very quick to print, but they don't have very much personality to them, and I thought if I have something that's a bit more 3D, it might take a little bit longer to 3D print, but it looks so much better. So let's go into that and have a look at some of the sketches that are involved there. In fact, if I've highlighted this one, you can see it's not made up of many stages. I go for the first sketch. That was simply just to get the measurements there of the slots. So they're like 6.5 from the edge. The whole thing there is 48 across, and I think these why can't we see the measurement on there? So it's 3 thick, and I'm not sure what that measurement there is. Let's just measure from there to there. I think it's about 8. There we go, 8. That's fine. And yeah, so that's the first sketch that I did, just to give it let me just go that, a bit of basis. And then what I then did is I extruded up just a block. So a block 30 centimeters, using the edge of the board as a guide. So I just created that sort of rectangular piece, extruded that up. So then the next thing that I did was then put in all the measurements. This looks a bit funky on there, of the rangefinder. So the key measurements on here is that one there, which is 17 for the diameter of the rangefinder, and I think they are 25.5 from the middle points. That seems to work fine. And what else have we got on there? And then there's a couple of cutouts that we need, because on the rangefinders, let me just grab one here. The rangefinders sometimes have, that's a really bad example because that one hasn't got it. The rangefinders sometimes have like a crystal or a capacitor. Let's just grab this one, there we go. That's an example of one that's got it on. So there's like a great big silver thing right between that thing there. It looks like a big capacitor. That can sort of stick out and stick into the design. And sometimes the pins themselves, they protrude a little bit, so you can't just have this completely flat, you need to sort of allow for them. So that's what these two rectangles here are, the top and the bottom. And then you can also see I've used the fit point spline to create this sort of organic shape, and I put all the key measurements in there just so that it locks into place. You can see there all the different parts of that are just holding those handles in place. So once I've done that, I can then use that to create a shape I can push through. So we can, so what I do then is I cut out that shape from the rectangle like so, just by doing a select and cut, and extrude that through. The next one is to cut out on the back of the rangefinder, cut out those little areas where the capacitor goes. So let's just finish that. And then next up we have the eyes, if you like, the holes. So we just push them through from the front. Oops, just lost my mouse then. So they're just being pushed through from the front, and then the next bit is the bottom of the rangefinder holder. So let's just get a close-up of this. So what I've done on here is I've created two little tabs that push through from the very bottom of the rangefinder holder there into those holes that we've already pre-measured. They're the ones that are 8mm, 6.5 from the edge, and it's 48 across the bottom there. And I've just extruded them down a little bit. Can't remember what that was. Let's just go to the thing and have a look. So that's 5mm down. You can see they're completely rectangular, but I have put a taper on there of -2 degrees, and that just means that they'll go into these holes a lot easier than if we didn't have that. They would try and go straight down, and guaranteed that'll cause a bit of issue. But 2 degrees seems to be enough taper for them to sort of be quite firm when they go in there, but it's easy to push them in and they stay in place. So the next piece then was just to add some fillets. So just add some fillets to the bottom of those tabs so that they're not quite as rectangular. And then the last thing I then did was just add some more fillets to this, just to round out the sort of face. So if I just go just before that, you can see that it's got quite a hard edge to it there. That edge there, so just by putting the fillet on there, makes it look really nice and smooth. And then what's the last thing I do there? Then the last thing I do is I push back ever slightly to add a bit of tolerance the front face of those tabs that come down, because I know from experience if I don't do that I'll end up having to sort of file these away with one of my sets of files. So if I do that in the part of the design, then it's going to work fine. So if I just double click on that stage there, we can have a look. It's -0.2. So 0.2 seems to be a good tolerance to make things fit with 3D printing. Probably because the width of the filament is like, what is it, 1.75, something like that. So 2 seems to be a good fit for that. Okay, so that's the rangefinder holder. So let's go back to the rest of the robot. Oh, I've moved the timeline out of sync there. Let me just make sure that's all good. There we go. It's forgotten about all the rest of the pieces. And grab that to the very end. There we go. And then let's just move that out there. There we go. So yeah, the other things I just wanted to show then was these motor holder pieces. So let's just have a look at one of those. There we go. Is that the first one? Where's that one? There it is. Okay, so I've actually designed this outside of this model and brought it in as a separate piece. We can actually go and find it in here. There we go. Rover wheel holder. So yeah, you can buy these from places like Pimoroni. They sell them with the nuts. Let's just throw a different colour on there for a second so you can actually see that a bit easier. There we go, you can now see a little bit easier the where the nut goes through. Let's just put the black one back on there. Oops. And we can then drop a nut in there, and then when this goes onto the other side of the chassis, so this is going on like, you know, the back of the chassis, holding the motor in place, we then screw the nuts through, that'll screw into that nut hole there. The captured nut will then tighten against the chassis, and everything's good and held in place. So these are really simple design, don't take very long to print. Probably need a little bit of support depending which way you would print them. I would probably print them in this kind of orientation, just because it's going to require less support. You're only going to be supporting those two sides there, whereas if you printed it the other way around, you've got to support this entire section here, which is probably not great. So yeah, if you were printing it that orientation, it would have to put support all there to sort of hold up that roof, and we don't want that. But they're really, really strong. I know this from this robot which I designed a while ago, and there's the version for them. The nuts on these ones are a little bit closer together. On I'm pointing there at the screen, you can't see this. On Rover, they are a bit closer together than they are on this one. But yeah, that works really, really well. So let's go back over to our robot and let's have a look what else we've got. So this is part of the design process that I go through. I've got designs for things like these N20 these N20 motors. I've modeled them up in Fusion 360. If I don't have a model for something, I'll go onto somewhere like grabcad.com, look for the model, bring that in, download it, upload it to Fusion 360. But it means I can bring in things like these, you know, the rangefinder itself. So I've got like a really accurate model of what a rangefinder looks like. So if I just move this here, if I select the very base one there and I just hide the rangefinder holder, you can look at that. Look how accurate that looks. It looks like the real piece, and it's even got every single chip on there, so you know all the tolerances, all the bits and pieces. If it works in the software, then it will work on the design that you're designing. So I've got a question there. What's the name of the software that I'm using to design all this? So this is called Autodesk Fusion 360, and there is an educational version of this which is completely free to students, to teachers, and also to hobbyists, which is really cool. This is how I first got using Fusion 360. So I think it works on Windows and on Macs. I'm not sure about Linux, but if you're using a Windows PC or an Apple Mac, then you'll be able to use Fusion 360. So you do have to apply each year for the free license. I think you have to apply for it once and then just like renew it, but it's zero cost. And the only differences are in this sort of drop down here where you've got different options. There's a thing called generative design, which creates these really crazy spidery designs for things. You basically put in what parameters you want the final design to look like, and it will figure out where all the strengths and weaknesses are and what the optimal shape will be to solve that problem. I don't think you get that in the educational version. The rendering one, if I go over to render on here, you probably have to see a picture where I've previously rendered out. So that one that's there, for example, you can render out really like photorealistic looking renders of your projects. You can do that in the educational one. The only difference is when I click on the render button here, I get two options. I can either use the cloud renderer, which sends my design up to Autodesk, and they will render it for me, but it will cost credits. So if I wanted to render this one, it would take less than 20 minutes. And it would cost 2 credits. And I think you get 100 credits when you buy Fusion 360. But you can do a local render. So you just use the power of your local laptop, and however long that takes to render it out. It's usually quite quick. I've not found them to be too difficult. And you've got a few different renderer qualities. You can do like a really standard quality, or you can do like a final one. And Chris on the chat there is saying you can use Blender to do everything like this as well. Absolutely you can. And I did a video a couple of weeks ago on how to take a model from Fusion 360, put it into Blender. Blender is completely free. If you go to blender.org, you'll find that, and you can render out like beautiful pictures of your models using Blender. It does take a bit of skill, obviously, but there you go. So let me just switch back on that rangefinder holder. So that's kind of the process I go through. I'll go onto GrabCAD, find a model of something that I want to bring in, if I haven't already got it in my little library there, and then I'll bring it into my model. And then using the joints, I then join everything together, lock everything in place. So then what we can then do, if I just move this back a bit, if I grab one of these wheels, I don't know if you can see that there, it's actually spinning them correctly. So as I spin these inwardly, that will be then strafing sort of, nope, that way, that way. The camera is mirrored, so whatever I do, it's the opposite on screen. So it's really confusing. So yeah, you can do really cool things with that. I often use this as well to do things like, if I go back to the design there, I can switch off this grid layout, so I just get like a nice white background. I can switch off things like the object visibility, so all these little things that were on screen disappear. And you can even do something like make it so it's a wireframe but only shows the visible edges. So you can make it look quite interesting like that. I actually take a screenshot of that, export it out to Photoshop, and then in Photoshop I've got a little set of filters that I've applied that will reverse that. So instead of being a black line, it's a white line, and it's transparent, so you can put it on a slide and it'll just look really, really nice. So there are a couple of things that I usually do with this, but let's put that back on shaded. And what else do we need to say about this? Yeah, so that's where the board will go that controls all this. And there's some little standoffs there. The standoffs are quite cute. So if we go and hide that board there, and then we go over to look at these little standoffs. So these are like these little hexagonal nuts. I think they're just 10mm high, and they've got the, I think it's 3mm inward inside piece. And yeah, that's essentially what I did with Explorer. So that's got a whole load of hex nuts, exactly this sort of same configuration there. You can see this sort of three stacked up there. And it just gives your board a bit of breathing space. It means you don't have to sort of start cutting holes into the board. You could cut holes into the board if you wanted to make it print a bit quicker, but you sacrifice some of the stability if you do that too. And I don't know if it actually would be quicker, because the 3D printer's got to do more detail. So that's the Explorer robot, and I did promise I would show you a clip of this in action. So let me show you the Mecanum Wheels in action. So if I just bring this up and go back over there, there we go. So this is when I recorded. You have to excuse all the junk at the side of the desk there. This is me like in project mode making things work. So there you go, it's going forwards, it's going backwards. It's going to spin round on the spot. Look how accurately it does this. It ends up exactly the same spot as it started. And then it goes sideways. It does the strafe thing. Look at the direction of the wheels. So on this side, they were turning inwards. We'll just go back to that and show you that again. So watch the left-hand wheels. They sort of turn inwards, whereas the right-hand wheels turn outwards. So if I just play that bit again there, you can just see. Maybe we can actually slow this down. Playback speed half. Let's do that. Let's get it to about there. So yeah, just keep your eye on the direction that the wheels are spinning in, and you can see there the Mecanum effect in action. So clever. You can see that's running completely on a battery. It's just running a script on the board, and yeah, that's the robot in action. So I'm going to be working on this a lot more. Obviously, I want to work on Mecanum Wheels Fusion 360 designed and then 3D printed Mecanum wheels. I love the wheels that I've got on it already. I just want to have an option so that if you haven't got access to buy these because they're a bit expensive, but you have got access to a 3D printer, you can print your own out. So that's what I'm looking for. Okay, so I think that's everything I wanted to cover off in this video. So if you're watching this on replay, this is the point of the video where I'll say thank you very much for watching, and I shall see you next time.